Well, thank you very much again, Byron. It's been a great pleasure to be back in Miami and to be here at this wonderful institution all day. It is, I reflect on this frequently, that it is such a privilege to be an academician and, to be able to pursue things that we're interested in and interact with young, very enthusiastic, very brilliant people, and I'm appreciative of that all the time, and this was just a very good example of that today. What I'm going to try to do for you tonight in the next 45 minutes or so is give you an overview of our vision of how to cure heritable blindness. And this is a bad problem. The problem is both common enough to be really devastating. There are at least 150,000 people in the United States that have the types of diseases that we're going to talk about tonight. That's a lot of people. They're facing blindness. They're frightened. They need some help. There aren't treatments for these diseases for the most part right now. But 150,000 people in a country of 334 million people is not very many, and so they are this little sliver of people that are easy to overlook with any sort of healthcare systems. And so I've been taking care of these people now for 30 years, and initially I thought that the problem was a medical one. And we just had to figure out the genes and figure out the clinical features and everything. And it became increasingly evident to me that there were sort of strategic issues and leadership issues and political issues and stuff that were going to be just as important as the medical ones. And so I'm going to try to give you an overview today of how I think this type of blindness will be cured. It is going to be cured. It is going to happen. It's going to happen pretty soon. And so that's my goal for tonight. So I'm happy. This slide is my favorite slide in the slide deck. It's a badge of honor. I've resisted this slide changing to something other than this slide. So we have no financial interest in anything we're going to talk about today. So I'm going to sort of build the story tonight around two patients. One of them is this young man who has CLN3 associated Batten disease, which, as you probably know, is a really terrible disease that presents with profound vision loss in the first decade of life and results in severe shortening of life. So most children pass away by the time they're 20 years old from this condition. And so I first saw his sister, and she's now light perception, and he still has what we call LP vision, LP standing for Lego perception. He can still hold little toys up. And so, we feel this urgency to create some type of gene replacement therapy to put in the eyes of people like him to try to protect their vision. And the other person has been my patient for so long. His picture is actually hanging on the wall of the clinic, fortuitously for this slide. And this guy has USH2A-associated RP that is so advanced that gene therapy is really not going to be of any help to him. And what he needs is new light-sensing cells put under his retina to get his vision back. So we're going to use these two patients to sort of frame the landscape of the problem. So what unifies these individuals is they both have Mendelian disorders of the retina. As I'll show you in a minute, there are over 100 genes that can cause a disease like this. The most common ones in that 100 affect 1 in 10,000 people, and the rarest ones affect 4 or 5 or 10 people in the United States. They're bad diseases. They can cause complete blindness and sometimes other systemic things, as we've just mentioned. And what we really, really, really need to be able to do is treat these people, effectively treat these people. And we need to treat them regardless of whether they're at the rare end of the spectrum or the common end of the spectrum. We need to be able to treat them whether they're just being diagnosed and still have a ton of vision, or whether they have very little or no vision. This is very important. We need to be able to treat them for less than or equal to $50,000 a person. There are a lot of corporate concepts out there that these conditions might garner a price of a treatment of $1 million or more, and the rationale is hepatitis C treatment costs X, and how much more valuable your vision is, Y, and that kind of thinking. But you know, the thesis of my talk this morning was that humans don't do exponents very well. And so you go, well, 150,000 people in the United States, $1 million apiece, $150 billion, 150B. The current budget before the 20% reduction of the National Eye Institute is $800 million, less than 1B. So, you know, it doesn't take a rocket scientist or a big medical economist to know that we're not going to spend $150 billion on these diseases. And I'd be happy to talk with anybody about what they think their target number is, but it's something like $15,000, right? So what we need to be doing is thinking about how can we use existing technology to get the cost down to something that we can really deliver it to everybody. So to sort of, you know, get the lay of the land, you know, you can't work on a problem if you don't know what the scope of the problem is. And so we recently did a study which basically reviewed 1,000 consecutive families from my clinic that came from all over the United States and a few foreign countries, just to see which diseases were most common and what the relative contributions were and things like that. The cool thing about this study is that 76% of people in this cohort, we were able to find their disease-causing mutation. And when Byron and I started together in Iowa back in the 1980s, that number was 0. Not a single one of these genes had been discovered. And so now, you know, 30 years later, we have 76%, so that's good news. Other good news, I think, phenomenal news, is that was an average cost of $980, 980, to find those 760 mutations. I was telling this story to one of my retinal colleagues, and he said, hey, that's like half an Eylea injection. So it's kind of stunning to think about, isn't it? You know, down there in the injection hallway, there are like empty Eylea vials about waist high, you know. So 980, just not a big number, not a big number. The bad news is that these mutations were distributed across 104 different genes, and I'll expand upon that here. Now, you know, probably the most daunting aspect of this study is the shape of this curve. You know, I was showing this to people and I said, this really cost us $5 million in 6 years to generate this curve, but it did. And what the deal is there are a few genes, 2 or 3 genes, that cause a large fraction of the disease in the cohort. So ABCA4 is the most common one, about 18% of the total. USH2A, second most common one. That's the disease the person on the wall has, 8%. And then it rapidly falls off to this long row over here, which are all less than 1%. And CLN3 is in there. And so when you just think, boy, that's going to be pretty daunting to go after with a corporate model. You know, I'm not so sure that this flat part of the curve is really going to be feasible for a commercial deal. So this shows you the number of patients predicted to be in the United States with each one of these things. So 13,000 people with USH2A associated RP and fewer than 550 with CLN3 of all ages. So the cool thing is that of these 104 genes, 75% of them, the cDNA is small enough to fit an adeno-associated virus, which is arguably just a solved problem, okay? It's already in clinical trials, so come on, let's turn the crank and get this going. We don't really have a great large cargo vector right now, but helper-dependent adenovirus, which we're working on, might work. And that's got a cargo capacity that will take care of every other gene on the list that won't fit into AAV. So the idea here is one of reusable parts. How can we devise some strategies? So the AAV will get the little stuff in, ACAD will get the big stuff in. Let's get the preclinical data we need for that. Let's just turn the crank and get through this 104 list. So the fabulous thing is that if you own your own manufacturing facility, you can make a batch of virus that'll treat 100 people for less than $5,000 a patient. Well, that's a real different number than $1 million, isn't it? So we've already made constructs for 11 of the genes on the list. And the CLN3, which is what the little boy has already been packaged, or have already been at the FDA with this thing. And we've negotiated a deal with the University of Iowa hospitals, which I think you could negotiate at other places, because the virus is being made with philanthropic dollars. We went over to them and said, hey, will you partner with us and let us do the surgery at cost? And so we think that we can make the virus, do the surgery, and have 10 years of annual follow-up for $15,000 a patient. And so this is the model, and I think we can do it. If we can do it, other people can do it. And so this is sort of our vision of what's going to happen over on the gene therapy side. With our existing manufacturing capability, we can make about one product per month. So that would still take a bunch of months to get through the whole list, but maybe another institution or two will help us. And here's the cool thing. This FDA deal was not straightforward, needless to say. But once you've done it once, the next design is, 98% the same as this design. So we're just going to reuse the strategy, reuse the documents. So really the rate limiting thing going forward is just doing the studies, having the physicians to do the surgeries and the people in the laboratory to gather the preclinical data. A significant problem, though, remains to be solving what I'll call the large gene problem, because as we discussed with the drawing of ABCA4 and S2A, large genes are important genes, and we need to be able to treat ABCA4 and S2A and others. So as I mentioned, we think helper-dependent adenovirus might be the way to do it. But this is maybe an esoteric question, but as you're sort of testing these different viruses, if somebody suggests this one or that one, how do you know if it would really work in human photoreceptors or human bipolar cells or human ganglion cells or whatever cellular target is important for the disease in question? And I want to just show you a really cool technology that we're real proud of. We have a great research iBank in Iowa that has been run by Dr. Rob Mullins for a number of years. We have a very high rate of eye donation in Iowa. And we are able to get the eyes to the laboratory sometimes in less than 2 hours after death. 2 hours after death. And here you see such an eye, and we're punching these little discs out of there and then separating the neurosensory retina. Can you tell down here on the bottom? You see that little translucent piece? That's neurosensory retina that's been peeled off of the retinal pigment epithelium. And amazingly, you can keep that retina alive in culture for 10 days to 2 weeks after the person died if you get the eyes really quickly. And so what you see here is actually living human retina that we're testing the tropism of viruses in. And so this is going to be the way that we're going to figure out which of the viral types and which of the capsid subtypes and so forth are best. On the top These are just GFP driven by CMV promoters. The top one is AAV2 and the bottom is this helper-dependent adenovirus. But look at the morphology. This is like, 10 days after the person is dead, but their retina is still living in tissue culture. This is another just, I think, beautiful slide of how well preserved the morphology is more than a week after the patient has died. Okay, so this is my friend and patient Leo. This was the day after he got his new Institute for Vision Research t-shirt. You see it still has the creases on it where he got it out of the manila envelope. And he took a little selfie, to send to us how happy he was. And so that's the good news. The bad news is if this guy looks at himself in the mirror right now, this is what he sees. He's got just a few degrees of field left, and in that tiny little field, sort of in one eye, he's still got enough acuity that he can make some stuff out on his cell phone, but pretty much he dictates everything now and needs to use sighted guide to get around and trips over the please wait to be seated sign pretty reliably. And if he's in a hotel or something, he has no idea which one's the shampoo and which one's the body lotion. And, he just is very visually impaired, as many of our patients are. So this is an image of his retina. So oversimplification of the wiring diagram of the retina, there are 3 neurons that go between photon capture and an action potential going to the brain. The photoreceptors on the bottom and the bipolar cells and the ganglion cells that generate that action potential. And in retinitis pigmentosa and many other ones of these outer retinal Mendelian diseases, the photoreceptors are lost, but the inner retina persists for a long time. So we've had some of my patients pass away and donate their eyes, and there's bipolar cell mRNA in there. There are seemingly viable cells in there after somebody's been NLP for more than 10 years. So the idea is to utilize that inner retina as the conduit to carry information from new photoreceptors that we make from stem cell-derived photoreceptor precursors. And I know that sounds like totally wacky, but this has been shown by a number of groups over the past 10 years. This is a study by my colleague Bud Tucker, who took retinal degenerative mice and made photoreceptors out of iPS-derived stem cells and injected them in subretinal space. And you see the untreated eye on the top with the ERG, and you see the ERG is restored with the injection of these cells. And notice that it's not just an A wave that you would expect from just the cells doing something in the subretinal space, but it's a B wave suggesting that there's been some synaptic activity. And you see that it's proportional to the amount of cells you put in there. Other authors have shown actually visual behavior in whole animals from studies like this. So this is the idea that all of this stem cell transplantation stuff is based on. So when you get to this point where you can make patient-derived, induced pluripotent stem cell-derived retinal precursor cells, you really have 3 strategic decisions to think about. Do you want to make the transplants out of the patient's own cells or not? There are pros and cons of both of those things. Do you want to put them on some sort of polymer support or not? And then if you have some treatment, are you going to go test that treatment in blind eyes or in sighted eyes? So those are 3 strategic decisions, and there are studies out there right now that have made different choices about each of these 3 things. At the University of Iowa, we've decided that now that we have the ability to make cells from the patient, that we just don't see any reason not to take advantage of that and perhaps minimize the need for long-term immunosuppression. What we know about polymer support is that a polymer-supported retinal precursor has a 50 to 80-fold, not 50 to 80%, 50 to 80-fold greater survival and integration than loose stem cells injected through a needle. So we have totally committed to the polymer support idea. And then lastly, we think that because these blind eyes have a pretty healthy looking inner retina, we think we ought to put these things initially into completely blind people for one reason, to really convince ourselves that it's doing something. So instead of sort of moving the person around the clinic and saying, well, he used to be 2,200 and now he's 2,100 minus one or something like that. I've been in this business long enough to I wouldn't believe that, Whereas if we had a person that was no light perception and then they actually could get some form vision and tell the slit beam of the slit lamp was up and down or left or right, or they could see some hand motions or something, I would really believe that. And then secondly, of course, we just don't want to endanger any sort of useful vision when we don't know whether it works or not. So that's the reason why we've decided to use blind eyes. So why autologous? I've already touched on this. Retinal allografts, meaning from individuals other than the recipient individual, are associated with extensive immune response. And, even in animals without prior retinal disease. So we don't want to immunosuppress young people for their whole life. We don't want to be in a situation where somebody would get an infection and you'd have to take them off the medicine, and then maybe their immune system would attack the neurons that you work so hard to put in there. So we've just completely committed to making the cells from the patients themselves. So what's the problem if you do that? So if you make the cells from the patient themselves, what's the problem? Yeah, they still have the disease that they had originally, but fortunately, with this other fabulous technology, CRISPR-Cas9 genome editing. And so, this CRISPR-Cas9 is not the most efficient thing in the world for those of you that use it. So if you have a dish of cells and you edit them, maybe 5% of the cells would be altered by the thing. So it's not so great at the moment for an in vivo approach to try to edit, tissue in the body. But the great thing about editing cells when they're at the iPS stage is you can clone the result. So it doesn't matter that it's 5% sensitive, because you just clone it and then find a couple of clones that have been corrected and grow up a mayonnaise jar full of it, and Bob's your uncle, off you go. So that's really a solved problem in our view. So CRISPR-Cas9 corrected patient-derived iPS cells. Those are just a list of some of the genes that we've already successfully CRISPR corrected. In fact, we haven't found a single target that we have attempted to correct that we've been unable to correct. So I don't think that is a remaining problem. The real problem is this. The problem of doing any of this stuff, either the gene therapy side or the stem cell side, is you have to make stuff for human beings under a set of rules known as good manufacturing practices. You have to keep track of every single oxygen concentration in every single incubator from the minute the cell hits the thing until it goes into the person's eye. It's really, pretty daunting. We were fortunate that Steve Wynn made a very generous contribution to the University of Iowa, and we used it to build this GMP facility for both stem cell and gene therapy use. And look across the bottom there. This is an important little line that we're very proud of. We don't use any protected intellectual property, nothing. It's all open source. And if somebody wants the blueprints of this facility, you can have them. If somebody wants the protocols we use this afternoon, you can have them. I was telling somebody about this one day, and he said, so what if somebody steals that from you? And I said, well, it'd be sort of like breaking into my garage, stealing my lawnmower, and mowing my lawn, you know, because we never intended to get in the manufacturing business, right? We don't want to be in the manufacturing business. We want the patients to have these diseases treated, and so if somebody would steal the idea and go do it for $15,000 a patient, hoorah, you know? But if not, we'll keep doing it until somebody tries to do it. So this is what it looks like when you make photoreceptor cells out of adult skin. You start off with skin fibroblasts and treat it with these 4 pluripotency factors that Shinya Yamanaka discovered and won the Nobel Prize for in 2012. And when you do that, you get these little colonies of induced pluripotent stem cells that basically are just like embryonic cells shortly after conception. And so if you take factors that have been discovered by developmental biologists to be present in the developing brain and sort of in vitro mimic the rostral end of the embryo in the tissue culture medium, then a little lump of brain tissue will form by about the 30th day, and it'll have these little eyes start growing out of the side of it. You see the 2 little eyes that are coming off of that thing? And I can tell you the first time Bud Tucker, my colleague who's doing all this stuff, he said, "Ed, you got to see this." And he reached into an incubator and pulled out this Petri dish and put it on the microscope, and you know, the full impact of a human eye developing from adult skin, you know, hit me, and I kind of had to steady myself and sit down on the stool, and I said, you know, that is simultaneously the coolest thing I've ever seen and the creepiest thing I've ever seen, you know? But anyway, lots of science is like that, isn't it? It's cool and creepy at the same time. But anyway, you can take a scalpel and cut one of those little eye cups off and continue to culture it. This is not for the faint of heart, you know, because you have to go in and change the tissue culture medium every 2 days or so for 200 days, okay, non-trivial. But as you do that, what you see is that these eye cups go through the standard developmental progression just like a human eye. All the markers change in the correct order at the correct times. And by the time you get up to 120 days, the red cells here are recoverant cells, so those are photoreceptor precursors, and you see this beautiful, you know, 3-layer retina. And so this is the kind of thing that you would then dissociate to get the retinal precursor cells for transplantation. But remember I told you that cells on a polymer do better than cells off a polymer. And the reason for that is there's this process called anoikos, which is basically apoptosis that's driven by the lack of cell-cell connection. And the stem cells don't, these retinal precursor cells don't really like being dissociated. They don't like being shot down the bore of a needle at warp factor 9. They want to be in a sheet and transplanted in a sheet. So there's this, the 3D printing technology now has just come so far, it's just breathtaking. This 3D printer is capable of printing 75 nanometer features. And so pretty much anything that you can design on a computer, you can print structures that have 10 micron holes in them. And you can print it out of dissolvable biopolymers like polycaprolactone and chitosan. So here you see it printed on a millipore filter, the same kind of millipore filter you'd use in the lab to filter 5 molar salt to get the bacteria out. And you see the little tiny holes here, those are 1 or 2 micron holes in the bottom of 10 micron holes in the printed structure. And so if you want to load this thing up with retinal precursor cells, what you do is put that millipore filter on something basically that's like a Wexel sponge, and when you layer this dissociated cell mixture over it, the capillary action of the medium going down through the holes draws the cells into the holes. And that seems, isn't that an elegant solution? Well, we didn't come up with that right away. You know, the printer is designed to print on glass, and we printed a whole bunch of these things on glass, and then you layer the cells on it, and they just float off the top. They don't go anywhere. And so not until we figured out that we had to print it on something porous and have the capillary action get the cells down in there, could we actually fill it up. But here is a little movie of a confocal photomicrograph showing these are human retinal precursor cells living in a dissolvable polymer with little 10 micron holes. And the idea of it is to have the polymer dissolve at about the same rate that the new cells will generate their interphotoreceptor matrix. So you have enough support that when you put it in there, the cells sort of feel supported and don't die because of lack of connection to other cells. But then over time, the thing just completely goes away. And then here's just the same data shown in a little 3D reconstruction so that you can get a feeling for what this thing would actually look like. So the idea initially, for the initial experiments, is to print a little disc of this thing, this stuff, maybe 4.8 to 5 millimeters in diameter. We think we can get about 500,000 retinal precursors into a 5 millimeter disc like that. And we've got some instruments that we've designed that are, basically the same as the instrument you would use for a foldable intraocular lens, same kind of idea where you roll the thing up so that you can put it through a small retinopathy and then a retinotomy and then unroll it on the other side. And so we got all that stuff, and so we need some practice patients. So because we're in Iowa, and there are 3 million people and 20 million pigs, and pigs have the same size eye as humans, and we have a nice pig model of retinitis pigmentosa, so we can actually operate on retinal degenerative retinas. We have this lovely pig operating room right down below our laboratory, which is arguably nicer than some human operating rooms, and that's because pigs are a USDA species and those vets don't screw around protecting their pigs. Here's our surgical team. I want to especially, we have our own Dr. Russell. I know you have a Dr. Russell, but we had one first. And Elliot Sohn and Ian Hahn, who are just these great clinician scientists. I think this photo where they were sort of kidding around, but it really just captures how much they enjoy what they do and how much they believe in it and how skilled they are. So here is a pig retina, and this is a post-op OCT. Can you see the little 1x3 rectangular implant in there? It's vertically oriented. And here's the thing under the retina. This is a degenerative pig retina, so you see the retina's pretty beaten up, and then you can see the little holes in the graft on the OCT, which I thought was pretty cool. But this is just to show you that you can actually mechanically lift this injured retina and get this thing under there and get the retina reattached. So we think this is really going to happen. So I said one more problem. I realized when I was making the slide that this was kind of wishful thinking, isn't it? One more problem. There's like a million more problems. But there is at least one more really big problem, okay? So I want you to imagine, we imagine this all the time. We sit around thinking about this all the time because, power of positive thinking and all that. But I want you to imagine that one day we put one of these things in the macula of a completely blind person, and 8 weeks later or so, enough synaptic connection has happened that they actually have some degree of form vision, and they go from no light perception to being able to reliably comment on a light, maybe a bright slit beam or something, but there's no question about it that some photoreceptors that we made out of the person's skin is subserving human vision. So we'd all be really happy about that, but what is going to be the immediate problem when that happens. So it happens, and the problem is, yeah. So we can make these things, I told you, they're very manual. They're like making Swiss watches out of individual parts that you would cut out of tin foil with a pair of scissors or something. You know, I mean, it's unbelievable how difficult they are. And we can, you know, with all of our personnel working around the clock, we could maybe make, I don't know, 15 of these things in a year or something like that. So that's okay if what you're trying to do is show that Charlie Lindbergh can fly across the Atlantic. I mean, how many do you need? You know, 4 or 5, 10, something like that. That's okay. But it is not okay if the purpose of this is to actually make a dent in the advanced form of this disease. So if throughput is our problem, what is the answer? What is the one-word answer? Okay, I like that money answer. That's the answer to everything. But after somebody backs the big 18-wheeler full of money up and drops it off, what do we buy with the money to solve the throughput problem? Robots. And the day to start thinking about the robots is not the day that the first graft works. The day to start thinking about the robots is before the first graft works for a number of reasons. One, for the throughput reason, but also, obviously, if you could make a whole bunch more of these things, you could also do a lot more science with the same number of personnel. So robots are going to be valuable no matter what. So there's my partner, Bud Tucker, the stem cell genius, and he's sitting in front of a thing that we have dubbed Skylab, because that's what it looks like, actually. It's a bunch of these biospherics units that are all bolted together. We had to take out a bunch of benches in this lab so the thing would fit in there. It's 16 feet long by 6 feet deep by 6 feet tall, and this is phase 1. So phase 2 of Skylab gets bolted onto this after the next 18-wheeler full of money shows up. So this thing is all unlike the GMP facility, which I showed you before, where you have to go in there, you know, all gussied up in the hazmat suit and all that stuff. It's 37 degrees in there, you're dying. This thing is up in the regular laboratory, and it's all basically GMP on the inside of it. So now you can just run around and do development work. And so the robot development is going to happen in these big biospherics units up in the regular lab. So these are a couple of movies just to show you. Let's see if I can make it play here. Basically, you can have these plates of cells, and the thing will go over and image the cells at high resolution, and you can teach the computer how to recognize iPS colonies as well as a human, and then the robot will go in and pick these colonies for you and put them in plates. And so this is really, really hard, demanding work. And if you're going to generate a whole bunch of iPS cells, this is one of the bottlenecks. And so if you can just, you know, put those plates on there and hit go and go back to your office and have it go through and pick lots of the colonies and have them be really, really good ones, this is going to be a major step forward. But the other thing you need to be able to do is you need to be able to do a lot of fluid handling, and you need to be able to feed cells and move stuff in and out of the incubator and everything. So this company, Denso, makes these phenomenal arms that just, they have all kinds of different hands you can put on them, and they move very rapidly. You see how fast they move, and they never make a mistake. And so the idea is to have about 3 of these Denso arms hanging inside that biospherics unit that can open the tissue culture incubators, pull the things out, feed the cells. We work all night, all day, 37 degrees, no sweat. And so that's what I think the future of this is going to look like. So the overview then of the thing is that there's sort of two arms of the thing. There's a gene therapy arm and a stem cell arm. The stem cells are important for both arms because on the gene therapy side, we're actually using the iPS-derived retinal precursor cells from the patients with the diseases to recapitulate the disease in vitro, and then we correct the disease in vitro with the gene therapy, and that's our preclinical data. So in other words, as many of you in the room know, not all human diseases will manifest themselves in mice or pigs or other animals, and many fields have been just completely stymied for years trying to get a suitable animal model. And our feeling on this is just there's no way we're going to do 104 genes if somebody's waiting around for some large animal model to show efficacy. So what we think is that it just has to be sufficient to show that the overexpression of the virus is not toxic to human cells, overexpression of the virus is not toxic to normal animal cells, and we're able to restore the presence of the normal gene product in human cells. And you know, when you have those three pieces of data and you have a currently untreatable super rare disease, I think we just need to go put, you know, this stuff into the subretinal space of some still seeing retina of one eye and then follow people for a long time. And then on the stem cell side, you know, we talked about that. We're going to make CRISPR-corrected retinal precursor cells, put them on a dissolvable polymer, roll it up like a foldable IOL, and put it through a retinotomy into the macula, and hope that there'll be sufficient synaptic formation to subserve useful vision. And we're going to try to do all that for $15,000 or less on the gene therapy side and $50,000 or less on the stem cell side. So I want, you know, we have a big team. There are 30 faculty and 100 staff in the Wynn Institute. We were fortunate to have our own Indy 500 car a couple of years. One of my patients' parents is a former winner of the Indy 500, Buddy Lazier. That's him sitting there in the middle. So we thought we'd use that, you know, because it's kind of cool. But I want to thank, you know, really all the people in the WIVR that work so tirelessly and believe in this mission and want to make it happen. But we really need to single out Bud Tucker, who is just a phenomenally talented young scientist, and without whom most of this real Star Wars stuff would not happen. So I'd be happy to take some questions from the audience. Yes, sir.
It seems like technology is moving forward quite a bit, thinking of how to deliver it to a large number of patients.
In the not too distant future, you don't have to choose. You don't have to choose, okay? Who are you going to treat first? Well, the first person to put one of these stem cell things in is a relatively young person who won't be endangered by general anesthesia and stuff, and that we might expect to have pretty good interretinal function, and that we'd have evidence of pretty good interretinal function on OCT and everything, that still have some extant choriocapillaris, that still have some extant RPE, although between you and me, I am not sure that cones really care that much about the RPE or the choriocapillaris. I don't think so. I mean, you know, in Best disease eyes, the photoreceptors are like just up there in space, seeing 20/20 for about 30 years. Like, hey, I'm just up here. You know, I can get my blood supply from the inner retina. So I think cones may not need all that stuff. But, you know, why stress ourselves? We might as well find somebody that's got some RPE and some choriocapillaris. And, you know, they need to be basically NLP for the aforementioned reasons. And we shouldn't be putting these things in sighted eyes until we think it works. But the whole idea behind the robot deal What do you think the scale up would be if we made those robots, just the kind of robots I showed you today? What do you think the scale up would be? So from like 15 a year to what? 500. 500. In the first round of roboticization in just a medium-sized lab, we think we can take it from 15 to 500, which makes you kind of surgeon limited, not graft limited. And the other cool thing about robots is, you don't put an ad in a newspaper in Phoenix, Arizona for an experienced iPS cell, person. You get some good technical people who can run the robot. So, the other cool thing about robots is you could then farm this out to other institutions where, people could make stuff. So anyway, one part of it is like we sit around thinking all the time about how we would never tell somebody that they couldn't have such a thing because we didn't have enough of it. That's an important thing that we're worrying about all the time, because we don't want, like we think that, that's why this $1 million thing bothers us, because if you had $1 million treatment and 4 people could get the treatment, you hadn't solved the problem. We have to make it where anybody that needs the treatment can get it. Second thing you talked about was, are children better than adults? I think it is definitely true for gene replacement therapy that the earlier in the course of a disease that you can treat somebody, the more likely it is to work. And I think it will be almost certainly true that there will be a point of no return where somebody still has a whole bunch of functioning photoreceptors, but basically the die is cast. And if you put a new gene product in there, the cells are still going to be lost for whatever reason. So I think early will be good for gene therapy. But there are going to be a lot of cool opportunities there, like, for example, Usher syndrome. So Usher syndrome right now is awful because it endangers both sensory systems and so on and so forth. But if you had a treatment, then Usher syndrome would be the best, because you could find the kids with newborn screening of the hearing loss, have an aggressive gene therapy program, and then basically have 10 years of warning before somebody lost vision. There are other things like MAC-associated RP, which is the most common cause of retinitis pigmentosa in Jewish people. It causes about 30% of RP in Jewish people. So we're envisioning a nationwide screening program, the main purpose of which would be to identify couples at risk, like a Tay-Sachs screening thing. In other words, put it actually on the Tay-Sachs screening panels. But what's the problem with a screening thing like that is you're going to cough up 22-year-olds who think they're being screened to find out if they're a carrier, and they're actually pre-symptomatic adults. Those pre-symptomatic adults are going to be great because MAC-associated RP, we've already shown that you can overexpress MAC and it doesn't hurt the cells, and it restores function and stuff. So in summary of all that, and maybe what I should have said first is it's just so exciting. We've been sitting there for 30 years just watching people lose their vision at various rates, hoping to find the mechanisms so that one day that we could intervene, not really knowing how we were going to do it and stuff. And now we're saying things like, like which patients would we do, and like in what order? Oh my God, how wonderful it is for us to finally be sitting around talking about that stuff. So did I answer most of that question? Okay. Any other questions? Yes, sir.
So how do you see the different approaches like
sort of the retinal chip, the cochlear implant for the retina, and this thing called optogenetics, in which you would express a light sensing channel in the intraretinal cells. So I think that both of these technologies are interesting. I think the scientists that are working on them are excellent. I think some of the results that have been gathered with them are promising. The reason that we aren't pursuing them at all, like zero, is that, you know, I think the cochlear implant for the retina thing is physically limited. The current device has 60 electrodes, not because you can't make them smaller, but because when you increase the charge density to the point where you actually generate photosensation on the other side, the size of the cloud of stimulation is too large. This is why the human retina didn't evolve to use electricity to signal. The reason the retina evolved to have synaptic connection is so that you could make the density of the detectors really, really packed in, and they could talk in a very small space. So I think that, you know, having living tissue that communicates with neurotransmitters at sort of the right scale is more promising than that technology. Regarding the optogenetics, let's just think about the mechanism of retinitis pigmentosa. Rhodopsin, one of the most common causes of RP, is what's the most common mutation in rhodopsin in North America? Does anybody know? Pro23 his. A missense mutation up in the N-terminal end causes misfolding of this abundant protein, the protein that's supposed to be in there, but it's just misfolded. And it sort of causes ER stress and over a period of decades kills the photoreceptor. A missense mutation in a normal protein that's supposed to be in that cell kills the photoreceptor. So now we're talking about taking an artificial protein, not normally in ganglion cells, and expressing that and altering the electrophysiologic behavior of that cell, okay? And then we imagine that the ganglion cell is gonna be okay with that for the long term. I mean, that interruption of the physiology of the cell seems about 50 times more aggressive than the missense changes that routinely kill the photoreceptors. In any case, so in our view, there's exactly one thing you cannot do, and that is hurt the inner retina. One thing you cannot do is hurt the inner retina. Because, like people say, I think one of the questions was asked, like, what if the synapses don't work or something? Well, okay, we're putting in cells that we're asking, you know, to grow a few tens of microns and form synapses. Like, if you have to somehow get cells from the surface of the retina to grow 8 centimeters and find their way into the lateral geniculate nucleus, that's going to be a challenge. So in our view, you want to, above all, not injure the inner retina. Because one of the cool things is, like, what if we put one of these grafts in somebody and it didn't work? What's probably going to happen? What's going to happen to the graft? I mean, the cells are probably just going to apoptose, you know, they didn't hook up, you know, just the graft wasn't very good. The polymer dissolves. There isn't any reason that you can go back into the same eye with version 2.1 or 2.6 or whatever. You couldn't put it in the superior retina, the inferior retina, 8 different places, as long as you didn't hurt the inner retina. Some of these mechanical things, I mean, those are pretty aggressive alterations of the eye. So, you know, if somebody was 75 years old, no light perception, and they wanted to, you know, put one of the Argus things in one eye, you know, I think that would be okay. But I don't think that eye is going to be a stem cell eye in the future. So if somebody was 40 years old, I wouldn't be fooling around with the inner retina. I would be waiting for someone to get a more biological, long-lived strategy.
Do you need healthy or functioning RPE cells to support
The question that you're asking, 3 diseases: central serous retinopathy, Best disease, and choroideremia. So a very interesting thing about, let's take choroideremia first. You see a choroideremia patient, and they come in and you look in there, you go, oh my God. You know, it's just like, it is so striking. There is like no retina in there. And they have this tiny little 400 micron diameter thing in the fovea. And they go over to get a Goldman visual field, and they come back and they have kind of like a pretty big Goldman visual field. Have you guys noticed that? The visual field in choroideremia patients is way better than the choroid and RPE would suggest. And I believe that that is because a bunch of cone photoreceptors don't need chromophore provided by the RPE. I think they get chromophore from the Mueller cells. They don't need very much. And there is tons of oxygen in the retina, in fact, too much arguably, provided by the inner retina. Sort of the same thing with Best disease. You know, we have these Best disease patients, they're 60 years old, they've had a vitelliform lesion for 60 years. Their photoreceptors have never been closer than about 500 microns to an RPE cell in their life. Those cells see 20/20. CSR eyes, the photoreceptors are a long way from the photoreceptors. So I think that if you get a bunch of cone photoreceptors in there and have some of them synapse, I think that they could subserve some sort of useful vision. Now, to make really useful vision and, you know, sort of rebuild the retina, then you might want to put everything in there. And we can already make choroidal endothelial cells. We have already made polymer supports for the choroidal endothelial cells. So you seed choroidal endothelial cells in these sinusoidal patterns to try to get them to form tubes and stuff. One idea that we have for that, okay, everybody hold on to your chair before I say this. We also had the idea of putting VEGF in there, not anti-VEGF, VEGF in the polymer where we're seeding the thing to like encourage the remnant choroid to grow up into this thing, sort of like the cheek pouch, you know, models to connect up the artificial choroid. The RPE is the easiest thing of all to make. You make this RPE, you get this beautiful hexagonal close packing with zonula occludens and everything. So we call that the tiramisu project. So the idea is that you would make the choriocapillaris, you would make the RPE and put that on top, and then you would make the retina thing, and you would put all those things together, and you'd put all of them in there. But that's not what we're going to do at first. We're going to just try to find somebody that still has some RPE and choriocapillaris and a bunch of healthy inner retina, and just try to put some photoreceptors in there. Yep.
Excellent talk. Congratulations on an amazing program.
Thank you.
And something you know how this is going to work when you transfer.
Well, I understand the question, and the question is, a question sort of comment is maybe our forceful belief in autologous grafts is a little bit misguided at present, and there are some other things we should think about. And, you know, obviously, whenever you're talking about, in a talk like this about your vision of the space program and how the lunar excursion module is going to bind to the front and then spin around and so forth, and you haven't done it yet, there are going to be things that don't work and that you have to overcome. And there's, I think, no doubt that there are some issues with iPS cells that are going to be a problem. Having said that, we have made these cell lines and done genomic sequencing, whole genome sequencing on the product, and there's not a lot of genetic, detectable genetic alteration in the cell. They're basically normal human cells. They look anatomically as good as the, fetal-derived or embryonic-derived cell. I mean, obviously, we're not talking about taking formed retina out of cadavers, right? We're talking about making those cells either way, and so they're, not perfectly normal and might be making different antigens. And we have data that I alluded to briefly. You know, if you put allografts into pigs, they're very aggressively attacked. And, you know, I was in a room one day and somebody, you know, who's not an ophthalmologist, and they were telling me about how, you know, the eyes immune privilege, had this big sign, eyes immune privilege. And I was sitting there going, dude, do you know that there's an entire branch of ophthalmology where we just sit around trying to save the eye from the immune system? You know, this is not like, you know, there are whole chapters in the textbook, immune system trying to kill eye. And I have some of my patients on 3 grams of CellCept and every 2 weeks IVIG, just because their immune system is pissed off at the retina that they were born with, you know? And so perhaps because of that experience, my choice is to come at it from the autologous side and see what we encounter over there. You know, also worthy of mention is like the renal literature, 50 years of renal literature. If you look at the survival of a kidney and graph that by the degree of matching of HLA antigens, it's a linear relationship between the matching. So for all those reasons, we've sort of just bought in on this autologous thing. But, you know, the reality is, I was giving a talk one day, and I was talking, you know, sort of all this stuff, waving my hands around about how we, you know, hope it worked and everything. And I said, but you know, if someone else makes this work before we do, is that a good thing or a bad thing? And there's this like pause, like it was a trick question, you know? And this lady in the back of the room said, it would be a good thing? And it's like, yeah. So it would be a good thing. So if anyone with any of these approaches that we've talked about, you know, that people ask about these other kinds of approaches, if anyone made any of those approaches work, I would put my patients in my car and drive them there myself. I would take the person out to dinner. I would dream up some award to give to them. You know, I mean, it would be great. And so if the unmatched stuff works, then we've spent a whole bunch of time trying to perfect the autologous stuff unnecessarily. However, if the non-matched stuff doesn't work, then we have put potentially inciting antigens into the subretinal space of young people. And that's the thing that we're trying to avoid. Yeah. So out of respect for everybody's time, I've kept you 30 minutes later than we should have. I think we should let everybody go home. And if anybody has additional questions, I'd be happy to hang around up here for a few minutes and answer them. Thanks again for having me.